vessel code, sections 1, 4, 8. There's a number of documents there. And that is I'll call it a soup to nuts design code. It's all about breakthrough materials, design, to testing, and then tolerances, all that. So Canadian code is the CSA B51, that's for boilers and pressure vessels, and then there's another one called the TEMA code, which is a tubular exchange manufacturer's code. All those are legislated codes that we have to follow. For specifications, it's not legislated. The American Petroleum Institute has specification 660 for shell and tube heat exchangers, and then we use client specifications and our own internal fabricator specifications. So those aren't law, but we do have to follow. I'm going to turn it over to my colleague now, Paul G.
Good afternoon, everybody. Hopefully everybody can hear me. My voice is not loud as Dave's. So we're going to talk about thermal design of heat exchangers. As you know, we're studying heat exchangers as so many types, right? Shell and tube heat exchangers, spiral heat exchangers, plate and flame exchangers, air coolers, economizers, as they said, you can name it. But as a company, Atex, we specialize in shell and tube heat exchangers. To design those, we don't do any hand cuts at you. But we use some softwares, HCI and ASPENTEC. So these are the pretty industry recognized softwares to design the shell and tube heat exchangers. So designing a shell and tube heat exchanger, we will get an inquiry from a client to design an exchanger to perform certain duty. As Dr. Raman mentioned that you guys love equations, so I put one in there. Q is equal to M times Cp times delta T. This Q is your flow rate, Q is your duty, M is your flow rate, Cp is your specific heat, and T1, T2 is inlet outlet temperatures. Important thing to note once you see this information always comes from client. They provide you the process information for shell side and for tube side. So shell side duty have to balance with tube side duty. So shell side duty is equal to the tube side duty, which is the duty of the exchange or heat exchange by an exchange. So what is the minimum data required to size exchanger? First of all, you need shell side and tube side properties. Without any properties, you can't size exchanger. For single phase fluids, it's much easy to size exchanger because you need just properties at inlet pressure and at inlet and outlet temperatures. The properties require density, viscosity, specific heat, and thermal conductivity. Once you have those, you're good. And once you have the shell side and tube side properties, the next thing is to come up with this certain geometry, what called TEMA type. What is going to be a front head? What type of shell we need? What type of rear head you need? So I think I handed out some TEMA charts as well. We were short for it. So if you look, the first column, these are the front heads. It shows A type, B type, C type, N type, D type. Every head has its own importance. Like A type can be used where you want a quick inspection of the tube and you want to remove the bundle. And you can replace that with cheaper B type head because you're not putting additional flange and cover on there. You just welding a semi-elliptical head. So depending on if you have high pressure exchanger, then you would want to use the D type head. The same thing on the second column, which shows the different type of shells you can have, like E type and F type. So E type is one pass shell, where F type is two pass shell. So if there is any temperature cross in E shell, you have to have two shells in series to eliminate that temperature cross. To make it cheaper, you can make as F shell. So you separated that shell into two shells. Then K type, it's a chemical boiler, as explains there is a lot of ventilation going on, so you need K type shell. Same thing on the rear heads. So how do you name exchanger? Normally, when we talk in industry, somebody will tell us 23 to 40 BU. What does that mean? So 23 is the 23-inch shell ID, and 240 is the tube statement, and BQ is the tumor type you selected. B is your front head, E is your shell, and U is your rear head. So that's the way you form a tumor type. So other things to consider once you have this information, you have to apply, as Dave mentioned, through customer specifications, all the ASME codes and nice stuff. A lot of inquiries you get when the EPC companies, the new engineers, when you guys go out, come up with the very cheap exchanger, but with a quite a bit long length of the tubes, which is not available in the market, or if it is available, it's available on special orders. Right? So that not reducing the cost, actually, that's increasing the cost. And it will be really hard to maintain as well, because if your tubes are plugged, you can't get the tubes in very quick. Tubing delivery is 22 to 24 weeks. So either you buy another exchanger, keep it spare. It can be done on special high pressure designs. Because in high pressure designs are the only designs you want to make them exchanges longer, not bigger in the diameter. Because if you grow in the diameter, every thickness due to the code, like flanges, your tube sheet, the stud diameter start going up. So you make it longer to keep it small diameter. As I said, you can get tubes more than 75 feet long as well. Practical problem. We, last year, 2010, we had one of our clients came with a problem. They had some plugging issues with one of their exchangers. Just keep plugging every 3 or 4 months. So they had to do chemical cleaning and stop the work, right? So downtime, that's money. So existing exchanger was 30-160 BEU with 3/4 inch 18-gauge stainless steel tubes. And falling factor 0.00352. Okay. Whenever we size exchanger, we always size for fully forward ignition. So this falling factor needs to come from our customer. They specify falling factor for certain tubes, and we always size exchanger in fully forward ignition. But when they fall more than they're supposed to, then they plug. So there is no read exchange. And the velocity on the tube side was below 1 meter per second. We're talking condensate cooler here, water exchanger on both sides. You guys have the tumor sheet. This is the improved design we had. So the solution we came up with, we put 1-inch tubes versus 3/4 inch tubes, and we taken out the U bends because most of the time it plugged on the U bends. We put the 1-inch tubes so you can mechanically clean it if you need to, and we put the more passes, like I think this one is 6 pass, and velocity we made it on tube side 1.47 meters per second. And good thing it's in service from here 4 months. So no phone call, it's always good. So no plugging issue. So this is the demat sheet. I wanted to show you the actual HDRI program we had, but some reason we cannot connect my laptop to the projector, so we had to miss out on that. So, any questions?
Any questions? I know we have lots of questions, so please ask.
Do you guys, for fouling, like, is there certain materials that, like, are more conducive to fouling? In terms of, like, do you guys pick certain materials to reduce fouling?
We don't check the materials.
You don't pick materials.
Material is specified by customer. Because it depends on their process condition, if they are exchanging in corrosive service or road. So they specify. Good thing in thermal design, we just have to specify the tubing material. That's carbon steel, stainless, Toflex. Fouling is when you run through liquid over a surface, it's a tendency to deposit. So deposit is called fouling.
An extreme example of fouling, Mike and I deal with quite often up in SAG is when you've got heavy bitumen from the oil sands, they will completely plug an exchange, absolutely plug it. Anybody that's worked for any of the oil sands companies, you'll see that. So
when you're designing, you want to design that with 90-degree pitch, so you can mechanically go into the unit. If you're designing on the tube side, you want to keep as we did in this case, we put 1-inch tube. Critical 0352 is the borderline for the tubing, and for the shell side, for the in this case, I think pitch is 30-degree. I guess I can point on the data sheet. If you guys look here, the layout is 30-degree. So, because the falling on the shell side is 0001. So if that was 000352 on the shell side as well, first of all, we cannot use any end-type exchanges because you can't open it up. It's a welded tube sheet on both sides. So you have to go with the removable bundle on that side. And you have to go with square pitch so you can take the bundle out and can do it again.
As the video shows the slide.
The animations that they showed.
What about configuration? As I see that first stack.
Configuration for the tubes. For the tubes?
I've seen that. Most you have in black is that.
Oh, like the pitch?
I think isn't that because we still not yet all so we have just covered that bundle of tubes. That's a different problem. That's not detected type of problem. So you will just whether it is standard mode or aligned mode, but that is different. That's not PSU.
What were the softwares you said you used for design?
Sorry.
What were the softwares?
Software,
Yeah.
HDI and AspinTech. AspinTech has a lot of products, and that particular one is Task Plus.
Yeah, Aspen also has the HYSYS, maybe we heard of HYSYS before. So this is a little further down in the design, like, we, I think design appreciate all the HYSYS. Yeah, that's the process now.
Any question from this side? I'm only asking from this side.
They're winning because we.
Yeah, maybe I'm standing on this side.
Yeah.
On the shell side, I know that there's a number of sticker codes.
Yeah, those are called baffles.
So how do you program those?
There is a TMA requirement. You have to have within 48 inch the maximum space you can go. You can go up to 60 inch, but the maximum recommended is 48. Because after that you have to start having some vibration issues. You can go a little smaller than that. But those are the baffles that help you increase or decrease your flow velocity to get the maximum heat transfer.
There's also different types of baffling arrangements, like the one that we showed is a single segmental, but you can have double segmental, you can have triple as well, so there's a whole variety of, and it's just all how you come flows. It looks like a perforated plate, so what we do is in the shop, we can take a circle, and then we cut it, and then we drill holes in it, and we stab it, shoot through it.
I think you said a typical flow velocity was in 1 meter a second.
It's for the water.
Okay.
For different fluids, it can be different. Like for water industries, that was close to 1.5 meter per second.
Why wouldn't
And
you
it
want to
always,
faster?
sorry,
Sorry, why wouldn't you want to go faster than that?
if you can go up to 2.6 or 2.9 meter per second. It depending on material. Like this one is stainless steel, you can go in there over 2 meter per second, but you want to hit minimum 1.5 to reduce the falling. But you don't want to go too much higher because that will start erosion issues.
Any other question? Any question?
For bitumen, if you're trying to pump bitumen with that, you pump it at significantly higher velocities than say water would, because it's very, very.
Yeah, no, not necessarily, but you want to heat it up. Yeah.
So you heat it up and then you
Yeah.
make it flow.
Yeah.
This.
I think the velocity of bitumen would be. Off my head.
These are too fast.
I have a question. Like when you design the detector, two things convey the message as a designer of it, like 5 or 3 parameters, which is the most critical in design, in design activity. And again, 5 or 3 parameters that you need to take into considerations from the safety point of view. So which are those points? Like cost, you mentioned the cost is one of the things. What are the other things?
Cost is the least, from a safety point of view.
Yeah. In terms of safety, it's inherent in the legislative codes that we have. It's such a highly regulated industry that I would think that, most of the checks and balances are already in place by regulations. So we have to follow very specific code designs, very specific welding and fabrication methodologies. And then we've got inspectors that are in our shop every day. So we've got government inspectors inspecting because, if you ever hear a story years and years ago about boilers blowing up, that just led to all these codes and standards. So from the safety perspective, I think from the mechanical side at least, on the thermal side, I can't really think much on the safety. Now your other question was on.
Design considerations. So costing would be one of the.
Then that is, yeah. Whether or not, I posed it in part of what I was presenting. Can it be fabricated? So, Baljeet alluded to it, the footprint. We have to be very cognizant of how big this exchange is going to be. You won't find as a rule, in the package of, and I forgot to talk about it, in the package that we passed out there, the biggest heat exchanger that we've ever worked on is about 13-foot diameter. So it doesn't get much bigger than that. So you've got to stay within a certain footprint. And yeah, because it's such high pressure.
We did that on slide 2.
Yeah. Yeah, that one on the side. So I'm not sure if that really answers the question. But yeah.
So,
Your pressure vessel, do you fabricate that or is that prefabricated?
No, we fabricate. Yeah. So it's a very distinct pattern that it follows. We deal with the client first, so they give us the process parameters, and we size it, and we interact back and forth with them. And then once we size it, then we mechanically design. They all kind of go hand in hand, but it's first thermal size and process design first, and then mechanical design. Yeah, and then we build it. We build it.
What's the average, length of time to build one of the exchanges?
Oh, it's quite a while.
It depends the shop availability, but if you say there's nothing holding up and all material is 6 to 8 weeks delivery, you're looking at one end we talk. It's a pretty small exchange. You can do that in 12 to 14 weeks. But if we're talking about, again, cost is the consideration, right? We're bringing tubes from China tubing within this 24 to 26 weeks. So after that, we need another 4 to 6 weeks to complete that.
So it's better to maybe make it bigger than expected. Just so it was required to get what 3/4 of the tube from each diameter. So it's easier to do.
That's it. C3 had the issues plugging on the U-bend. We probably had used 1-inch tube with the U-bend as well. The only reasons we didn't go with the U-bends, in any end type, we put fabric on both covers. So in half an hour on both sides, you can open the covers, inspect the tubes, and if you have to do mechanical cleaning, you can push the rods in, do